Hi, welcome back. My name's Michael Chandler-Page, a system engineer here at Cirrus Logic, and in this second video of the series on the 55nm ADC, I'm going to talk about how we exploited the small size of digital logic on 55nm to solve a long-standing tricky problem for pro audio product designers. It's called hybrid gain control. So, here is a problem that many designers of pro audio gear are going to be intimately familiar with. How do you control the gain digitally of an external mic preamp in order to have the continuous gain response feel like a potentiometer in the old days, and also to control the gain without it popping and clicking as you change the gain? It sounds like a simple problem, but anyone who's actually tried to design this knows it's definitely non-trivial. And the way we see it often implemented in pro audio products is using a system like the one shown at the left here. So we have a mic preamplifier in the signal path before the ADC that has its gain digitally controlled by an analog multiplexer switching different value resistors into the preamp circuit. What this means is that the gain is set in discrete steps. So as the user turns the gain control knob on the user interface for the product, the gain increases in these discrete steps as they turn that knob, which is most unlike the potentiometer in days of old. So in order to make it feel more like a pot, what we often see is a digital interpolation gain implemented somewhere downstream in the signal path from the ADC that it interpolates between these analog mic preamp gain steps under software control. So the way this typically works together is that, imagine the user turns that gain control knob to monotonically increase the commanded gain. So that's shown in the graph at the top right there. And then underneath it, you can see what the mic preamp analog gain does. It goes up in these discrete steps as the user turns the knob. And then in the bottom graph there, you can see what the digital interpolation gain is doing, ramping up between those steps, and then when the mic preamp gain steps up, the digital interpolation gain has to step down at the same time. Now the problem here is that if there is any time domain misalignment between the analog up step and the digital down step, you get a glitch caused by a gain change transient on your audio, and that glitch causes an audible pop. And this is a hard problem to overcome when the digital gain is implemented in a different part of the system to the mic preamp gain control. And also, as you can see from the system on the left there, there's a lot of stuff going on, right? This is complex to implement, and it can also be quite costly to implement if you try to find a way of precisely time aligning the mic preamp gain change and the digital gain change. So as we learn more about this problem from our customers through the process of developing this ADC, we came upon an idea to make this much, much easier. We've integrated into the ADC an analog zero-cross detector in the ADC front end itself to synchronize analog gain changes. We have a SPI controller that is daisy chain compatible in the ADC chip to directly control the gain of the external mic preamp. We've got a digital interpolation gain after the ADC, and then we've got a controller to synchronize all these components together. So the way this works is that when the host processor writes into the ADC chip the register commands to change the gain of the mic preamp, first of all, the ADC sends out to the preamp the pattern of bits over SPI in order to set the multiplexer to the new gain value, and it keeps chip select asserted low. It waits until an analog zero cross is detected in order to deassert chip select, terminating the SPI transaction, which causes the mic preamp gain change to take effect. It then executes a very precisely timed digital gain step in the opposite direction to compensate for it, and then the digital gain ramps to the new target value. So because we have now in the ADC chip direct control of both the mic preamp analog gain and the digital gain, it's possible to synchronize those two events together with absolute sample accurate precision, which means that you get click-free gain changes. The registers to control all this have been designed to be easy for host software to interact with, and this works with any mic preamplifier design that implements stepped gain control, because the gain steps are completely configurable and the pattern of bits to control it is also configurable. Now, taking a step back from all this, this is a big complex digital feature. It increased the gate count of the ADC chip by about 10%, but because on 55 nanometer digital logic is so small, when we added this to the design, it just kind of squished into the existing digital region of the chip layout without actually growing the die size or the cost of the product anymore at all. So, thank you for listening. In the next video, I'm going to talk a bit about how we got performance improvements for the ADC itself from the 55 nanometer process.